In this video, we will understand about CMOS inverter transfer characteristics. Transfer characteristics is simple, it is output voltage versus the input voltage. But the very first point, I want to make sure that you know all your basics right, because this is the very important topic, the 5-star rating. So make sure you understand this topic in depth. First, you should know about the circuit of the CMOS. We have already studied in our basics, but that was the ideal condition. If you provide the 0 volt, you are getting the 1. If you are providing logic 1, you are getting the 0. It behaves as the inverter. That's true because it is ideal, but practically it's different. Your input voltage will have the different stages, different voltages, and you will get the output voltage as different at every stage. That is very important in the CMOS inverter transfer characteristics. We have to look whether our PMOS is in which region at what time of the input. If my input is at the 0 volt, whether my PMOS and NMOS are in linear, saturation or cutoff region. We are interested in that knowledge. Okay, first point is you should know that the CMOS is called complementary MOS because at the upper side we have PMOS, lower side we have the NMOS. So complementary MOSFET we are using, that is the reason it is called CMOS. And the next point you should note is we have the 4 voltages: VGS of P, VGS of N, VDS of P and VDS of N. Now these are the 4 voltages. Every voltage have their uniqueness. They are not same. They are not same. So what are the uniqueness? Let us see that. VDD is 5 volt, VSS is 0 volt. Now these are the upper and the lower voltages, VDD and VSS. So they are 5 and 0 volt, but VGS comma N is input and VDS comma N is output. So now we will see why VGS comma P is equal to minus of VDD minus V input. Very important point. We have to understand one thing, that VSG is the standard notation when we write PMOS, and it is actually VS minus VG. So you have to check what is the source voltage for the PMOS. It is equal to VDD. And what is the gate voltage for the PMOS? It is equal to V input. So VSG is equal to VS minus VG, which is equal to VDD, correct, and minus V input. We have seen here that we have the VDD at the upper side and VG is equal to V input. So if you are writing VGS, that is the opposite. If you are writing VGS, then it is minus times VSG. So that is the reason you are getting minus of VDD minus V input. Similarly, you can find it for VDS comma P. If you go for the standard notation, it is VSD. VSD is VS minus VD. So what is the source voltage? It is VDD. And what is the drain voltage for the PMOS? It is output. So basically Vs minus Vd is actually, it is VDD minus V out. But you are writing in the format of VDS comma P, then it would be minus of VDD minus V out. So this is the reason, this all the notations you should know how they came up. You should not rectify these things. You should know exact meaning. So I hope all the notations are clear. Why VGS is N? Because it can be written as VG minus Vs for the NMOS, and you can see here when you are talking about why VGS comma N is V input, your VG value is V in, but your Vs value is ground. So VGS is equal to VG, which is equal to V in. So that is the reason VGS comma N is equal to V input. Similar goes for the VDS comma N, and I hope all the notations are clear up till now. But I want to make one assumption. The threshold voltage I am using, VTN, is equal to 1 volt and VTP is minus 1 volt. And if you have take the common threshold voltage, it is mod of VT is equal to 1. Now we can understand our basic idea about the transfer characteristics for the CMOS inverter. So the case number 1 is your V input is at the 0 volt. If your V input as the 0 volt, you will get the V output as 5 volt. And your assumptions was VTN is 1 volt, VTP is what? VTP is minus 1 volt. These are your assumptions. Now you are checking in all the conditions, you are checking how my NMOS and PMOS are behaving. You are checking this condition. Now we will talk about the NMOS. My VGS comma N would be what? From the previous slide we know that VGS comma N is equal to V input, and V input here is 0 volt, and your 0 volt is less than your threshold voltage because your threshold voltage is 1 volt. So if 0 volt is less than threshold volt, this means your input is less than your required threshold volt, your MOSFET won't be on. If your MOSFET won't be on, it is off, this means you are in cutoff region and your drain current is 0. So first case, your NMOS is in the cutoff region in the case number 1, where your V input is 0 and V output is 5 volt. But what about the PMOS? We want to see the condition of PMOS as well. So in which region your PMOS is working? Let us find that. VGS comma P is equal to this condition, that is minus time VDD minus V input. You do the calculation, you know every value. VDD is 5, V input is 0. After the calculation you will get minus 5 volt. Similarly you can find it for VTP. VTP is given, it's simple, VTP is given, that is minus 1 volt. So you have VGS comma P and VTP, you have to check the condition. So VGS comma P is less than VTP, but in the PMOS style you have to say that VSG, which is 5 volt, is greater than 1 volt. So you should know this style, because here you can say your transistor is on because your input is greater than your threshold. This is the correct style. Okay, and you can say this style is useful for calculation purpose, but this style is important for the conceptual purpose, to find whether your region is in linear, saturation or cutoff. So here your MOSFET is on. If your MOSFET is on, your next task is to ask yourself, if your MOSFET is on, whether it is linear or saturation region. Now we will find that. To find that, you have to check your driver voltage and your VDS. Always we did that. We have found the driver voltage and the VDS. We checked the condition greater or less, and then we commented on the answer. Similar thing we are doing. VDS comma P is this equation. Substitute the values. VDD, you know, 5 volt. V output is 5 volt. You will get the answer as 0 volt. Similarly, you have to find the driver voltage, which is VGS comma P minus VTP, or you can say VSG, and you should do VSG minus mod VTP. Then also you will get the answer. Do anyway, you will get the answer as minus 4 volt. And once you get the answer as minus 4 volt, you have to check in the sense of the NMOS style. If you are going for the NMOS style, you will get this, because it was easy for the calculation purpose. But if you want to go for the knowledge and conceptual purpose, you should check this condition, which is VSG comma P and VSG of P minus mod VTP. So this is the conceptual, where you know if it is less, it is linear. But if you are going for the calculation style, your signs, your style would be opposite. If it is greater, because you are choosing the NMOS style, so if it is greater, it is the linear region. And I have covered this in my basics. I have already said you how you can deal. Either you go for the calculation style, that is the NMOS style, then you have to consider your conditions opposite. So this is the style 1. And the style number 2 is you go for the PMOS style, and if you going for the PMOS style, everything remains same as you studied for the NMOS. So this is the style 2. I always prefer style 2 because conceptually it is easy, but for the calculation purpose, as you can see the step 1 and step 2, I followed the NMOS style. To go for the PMOS style, what you have to do, you have to change your VDS to VSD. Simple. You have to change your driver voltage to, if it's the driver voltage of the NMOS style, change it to driver voltage of PMOS style, which will have the minus sign present. So change the sign. If you are minus 4, it would be plus 4 for the PMOS fashion. And 4 volt, you have to check that 0 is less than the 4 volt. Yes, and it is the linear region. So in the case 1, we have studied that when my input is 0, my NMOS is in cutoff region and my PMOS is in linear region. Now I will increase my input voltage. So you can see that V input is similar to or greater than 1 volt. Then my output will be, let's say, similar to 5, or it should be something less than 5. So this is my case, and I want to check now my NMOS and PMOS would be in which region. So it would be interesting. Let us see first the NMOS. So VGS comma N is equal to V input. So you can say that VGS comma N is greater than equal to 1 volt. Similarly, we have the threshold for the NMOS as 1 volt. You can say that your VGS is greater than the threshold voltage, so your transistor is on. If your transistor is on, it can be linear or saturation. So we are checking whether our NMOS is linear region or our NMOS is in saturation region. So how we check? First we need the VDS, and then we check for the driver voltage. So VDS comma N is equal to V output. It is similar to 5 volt or something less than 5 volt. So this is our case, but our driver voltage is VGS comma N minus VTN, which can be written as 1 minus 1, and that is equal to 0, because the values we always know that VGS comma N, we know that it is input, which is similar to or greater than 1 volt, and VTN, the value is already, we have assumed that the value is 1. So 1 minus 1, the answer is 0. So surely 0 is less than 5. What does this means? This means that your driver voltage is less than your VDS. So if VDS is greater than driver voltage, you are in saturation region. So your NMOS is now in saturation region. So this is interesting. Now we will check for the PMOS. Now we will check whether our PMOS is in linear, cutoff or saturation region. So how to check? Our first step is always about whether our MOSFET is on or off. If it is off, then you are in cutoff region, but if it is on, then you are in linear or saturation region. So we always follow the two steps, and for the PMOS we take a special care. While concluding the answer we follow the PMOS style, but while doing the calculation we follow the NMOS style. So you can see the first step VGS comma P. So this is the NMOS style, and VGS comma P, according to our equation, it is equal to minus, this is VDD minus V input. So the answer is minus 4 volt. Now you have to check in the PMOS style. So you are checking your VSG comma P value, which is the plus 4, because VGS was minus 4. So VSG would be minus of minus 4, that is plus 4. And mod VTP is 1, so 4 is greater than 1. This means your transistor is on. If your transistor is on, it can be linear or saturation. So tell me, what is the answer? Second point is checking the region. So how to check the region? Find the value of VDS comma P. So again it is the NMOS style of calculation. So it is minus times VDD minus V out. You will get the answer as 0 volt. Now you have to find the driver voltage, which is VGS comma P minus VTP. You can note here it is not mod VTP. Mod VTP is when you do the PMOS style, but this is the NMOS style. You have to write the negative of the value. So you will get VGS comma P, which is minus 4, and VTP is minus 1. So completely it will make it as plus 1. So minus 4 plus 1, you will get the answer as minus 3 volt. Now what's next? You have to check your driver voltage and your VDS value. If your VDS value is, now you have to check in two style. Either you can go for the NMOS style because you have done the calculation in NMOS style, or you can change this value in the PMOS fashion and check the PMOS condition. So I will always prefer for the PMOS condition. So you can see that VSD comma P, this means I am changing the sign because my VDS was 0, so VSD would be also 0 because 0 never has its sign. Now what about the driver voltage? Driver voltage has minus 3 volt. So it will also change its sign because we are dealing with the PMOS, so we have to change its sign. So minus 3 volt will be 3 volt. Now we can say your 3 volt is greater than 0 volt. This means your VSD is less than driver voltage. You can say it is in linear region. So conceptually in NMOS and PMOS, the condition remains same, but you have to follow this PMOS style to make sure your conditions are same. So this is very important. This I have already covered in my previous videos. Why you should you always have two types. This I have already covered. Follow the NMOS style for only calculation, but go for the PMOS style while concluding the answer. Like I have concluded, my MOSFET is in linear region. Now we will move forward. Now this is the case 3. From my input is similar to greater than 1, my input is changed to 2.5. If my input is 2.5, I am getting the output as 2.5. So this is the special case. Now you have to check whether your NMOS is in which region and your PMOS is in which region. So for the NMOS, we will follow the same two process, MOSFET on or off, and then we will check for the linear or saturation. So first step, your VGS comma N is equal to V input, which is 2.5 volt. Now your 2.5 volt is greater than this threshold, that is 1 volt. This means your transistor is on. Now the next task is to check the region, linear or saturation. So VDS comma N, this is the V output, which is 2.5. The driver voltage is this, and after doing the calculation you will get 1.5 volt. So 2.5 is greater than 1.5. This means you are in saturation region. So our NMOS is in saturation region. What about PMOS? So now we will check for PMOS. Again we have to follow the two steps. First step is VGS comma P, that is equal to minus VDD minus V input, and the answer is minus 2.5. Now you have to check your transistor is on or off in PMOS. So this is the PMOS logic for the transistor on. What is that? VSG comma P should be greater than mod of VTP. So already you have VGS. To find VSG, change the sign. So you will get 2.5 volt. and mod of VTP is mod of -1, so the answer is 1. So yes, 2.5 is greater than 1, then your transistor is on. If your transistor is on, which is the region? Let's check the region. So what is the first step? VDS comma P. This is equal to minus VDD minus V out. Just substitute the values, all the values you have, the answer is minus 2.5. Driver voltage, substitute the value, you will get the answer as minus 1.5. To get the condition, you should be in the PMOS fashion now. You got VDS, find the value of VSG, change the sign, so minus 2.5 becomes plus 2.5. Now you have the value of driver voltage, change its sign, because driver voltage is actually for NMOS you follow this style, for PMOS it changes its sign, so minus 1.5 will change its sign to plus 1.5. Always do the calculation in NMOS. While dealing with PMOS, what you have to do? Change sign. Simple logic, you have to follow this, you will never fall in trap. So 2.5 greater than 1.5, so your answer is saturation region, because your VSG is greater than driver voltage. Now the case number 4 is interesting. Your V input is gradually increasing, so V input is similar to or greater than 4, whereas your V output is similar to 1 volt. Similar, or you can say similar to 1 or less than 1. So what would be NMOS and PMOS in the form of region, saturation region, linear region? So you have to find that. What you can do is follow the two steps. So VGS comma N is V input, it is similar to greater than 4 volt. Surely your 4 volt is greater than your threshold value, so transistor is on. Now you have to note whether your NMOS is in linear or saturation region. So VDS comma N is equal to V output, which is similar to or less than 1 volt. Then you have your driver voltage as VGS comma N minus VT, and substitute the value 4 minus 1, the answer is 3 volt. So you can say your VDS is less than the driver voltage, because 1 is less than 3, and that is the reason your NMOS is in linear region. Now we will deal with PMOS. So VGS comma P is equal to minus VDD minus V input, you will get the answer as minus 1 volt. Then VSG comma P, you have to find that value, that means inversion of what we have done. So invert the sign, you will get plus 1. Mod VTP is also plus 1. So actually we have done this, that it should be greater than or similar to minus 1. So this value is greater than or similar to this, correct? So basically it's greater. So if it's greater than, your transistor is on. You should have your VSG, that is the input for PMOS, greater than your threshold voltage, then only your MOSFET would be on. So here, yes, it is similar to greater, this means it is a greater, and your MOSFET is on. Now check for the region. So to check the region, it's simple. What you have to do, two steps, VDS comma P and VOP, which is VGS comma P minus VTP. Substitute the values in both the cases, minus 4 volt of VDS comma P, 0 volt for driver voltage. Do it in the PMOS style, which means change the sign. So VSD comma P, the answer is plus 4 volt, and change the driver voltage sign, it is again the 0 volt. So 4 is greater than 0, so your answer is saturation region, because your VSG is greater than the driver voltage. So the last case we have is the case number 5, where your V input is maximum, that is 5 volt, and the output is super minimum, that is 0 volt. So let us check for the NMOS, in which region the NMOS is working. So VGS comma N is 5 volt, VTN is 1 volt, so 5 volt is greater than 1, your MOSFET is on. Next step, VDS comma N 0 volt, driver voltage is 4 volt, so 0 volt is less than the 4 volt, so it is in linear region. So this is interesting, again you got your NMOS in the linear region. So we will deal with PMOS now. To deal with PMOS, you should first find the VGS comma P, which is minus VDD minus V input, so the answer is 0 volt, but your VTP is minus 1. So your VGS is 0 volt, so VSG would be what, 0 volt again, but your VTP is minus 1 volt, so mod VTP is 1 volt. Check this too. Your VSG comma P is what, 0 volt, your mod VTP is 1. So what is the relation? The relation is your VSG comma P is less than mod VTP. This means your MOSFET is on, off, and if your MOSFET is off, this means you are in cutoff region. So here in case number 5, the PMOS is in cutoff region. So this is the DC characteristics of the CMOS inverter. Y axis has the output, X axis has the input, and these are the 5 cases when V input is minimum, that is equal to 0 volt, it's similar to 0 volt, then it's similar to 1 volt, then it's similar to 2.5, then it's greater than 2.5, then it is, in the fifth case it was super maximum, that is the 5 volt. So these were the cases we covered. I just wanted to remind you about the cases we have dealt with, and we have seen how our MOSFET works in each case. In each case, NMOS and PMOS have different working, but only in the case number 3, NMOS and PMOS had the same working, that is the saturation region. So here are some notations. This value is VTN, that is the threshold voltage of NMOS, and here somewhere here you will get the VTP, threshold voltage for the PMOS. Then you have the VIL, that is the input low voltage, input high voltage somewhere here, and you will have the middle value as VDD by 2. That's what we considered in case number 3, similar to 2.5. And then we have this input high voltage, we have this VDD plus mod of VTP. Here we have to take the positive value of the threshold, and lastly we have the VDD, where when my input is high, super high, that is VDD, then my output is 0. So this is the curve. This represents the transfer characteristics, DC characteristics. Now we will see what were the regions. These were the regions 1, 2, 3, 4, 5, correct, and how our MOSFET worked in these regions. So this is the conclusion. In the case number 1, where my input is minimum and my output is maximum, that is VDD, then my NMOS was cutoff region, PMOS was linear region. Here when my V input is similar to greater than 1, then my V output is less than 5 volt, then my NMOS is in saturation, PMOS is in linear. When V input and V output are same, that is 2.5, the answer was saturation. And the fourth condition, when my V input is greater and V output becomes less, that is V input is greater than 2.5 and V output is less than similar to 1, then my answer is NMOS is in linear, PMOS is in saturation. And at the last, when my V input is maximum 5 volt, then my output is minimum, that is 0 volt. So you can say your NMOS is in linear region and PMOS is in cutoff region. All the calculation we have seen. So I hope you had the brief idea about CMOS inverter DC characteristics, and these are the some of the points you should know, so that whenever you are dealing with the drain current, you know exactly which equation to use. Because if you are dealing with the drain current for NMOS and the drain current for PMOS, it won't be same, it would be different. At some position, let's say case 2, you have to use the drain current for saturation region for the NMOS, for the PMOS it would be linear region. So these are the important point. That is the reason we have studied the practical working of the CMOS inverter. So practically it will work in this 5 condition. So this is all about the CMOS inverter. I hope you enjoyed this video.
तो फ्रेंड्स, अगर आपको मेरी वीडियो पसंद आ रही हो देन टू लाइक दिस वीडियो, शेयर विथ योर फ्रेंड्स एंड सब्सक्राइब टू माय यूट्यूब चैनल. तो मिलते हैं अगली वीडियो में. टिल देन टेक केयर. दिस इज श्रेनिक जैन. पीस आउट.